Hello everyone. With this video we're going to start chapter 13, which is really starting to get deep into kinetics. So up until this point we've really talked about the energies of reactions, and now we're going to start thinking about how fast reactions are. And in this video I hope to provide you with some vocabulary and just a introduction to kind of what we are working on through this chapter. Okay, so in order for reactions to occur, we need a few things. The big thing is that the reactants must collide. They must run into each other. And whenever they collide, they must have the proper orientation and the proper energy. And so these pictures are trying to show you the orientation challenges that can occur. So if we have, this is HF plus Cl goes to form HCl plus F. For this reaction to occur, our chlorine must collide with this H. And since this HF is small, that there are a lot of orientations of the HF that can occur in still allowing the chlorine to be able to find that H and undergo the reaction. Whereas in this reaction, where we have CF3 with an H plus Cl, trying to make, I think, CF3 plus HCl. I'm missing a C here. That in this reaction, the number of possible orientations that this larger molecule has to be in order for the chlorine to find this H, there's that orientation is much harder to achieve because that H is hidden within the whole structure of this molecule. And so this is trying to show us that we would expect this to be slow and this to be fast, because this one will be slow because getting that collision to occur with the proper energy and orientation is going to take a lot more chances because these collisions are random. And so there's a higher probability of reaction A occurring due to the smallness of the molecules. Therefore, it will be faster than B that has a lot of steric hindrance and a lot of orientation challenges to the reaction. Okay, so when we measure reactions, thermodynamics provides us the energy difference between the reactants and products, whereas kinetics is going to allow us to provide the speed of the reaction. And now, to get a full view of a reaction, we are going to need to understand both the thermodynamics and the kinetics. And it turns out that there is an interplay between these two properties, these two characteristics of reactions. And throughout this chapter, we're going to try to figure out how to understand when something is kinetically driven versus when something is thermodynamically driven. Okay, so in order to understand the speed of reactions, we have to monitor the reactants and products. A lot of times we like to watch the amount. And so to monitor the amount, we would watch the molarity or the pressure of a specific reactant or product. And so to represent this so that we don't have to have units flying around everywhere, when we put a species in square brackets, this is going to represent usually the molarity, but it can also be the pressure if we're working in the gas phase and not the solution phase. So watch for those square brackets and know that that is a representation of concentration or amount. The other thing that we are really working towards is to understand this reaction velocity. This reaction velocity is the rate at which a reactant is used or a product is formed. This value is dependent upon the reaction stoichiometry. And so this reaction velocity or the rate is given by 1 over, this is the stoichiometry, times the change of the concentration of species I with respect to T. Or if we have this V, this is volume, if we are working in terms of pressures. So what does this mean? This means that if we have 2H2 plus O2, it goes to form 2H2O. The rate of this reaction, the reaction velocity, is going to be equal to negative 1/2 times the rate of change of H2 with respect to time. But this is equal to negative 1/1 times the rate of change of O2 with respect to time. And it's equal to a positive 1/2 rate of change of water over time. Now notice that the water is positive because it is a product, because this is something that we are forming, whereas the reactants are disappearing, they're being used up, and so their rate of change is negative. But the key part of this reaction velocity is V, nu, is that it doesn't matter what we monitor concentration-wise, we should get the same rate, just normalized or corrected for the stoichiometry. Okay, now those reaction velocities kind of get a little complicated. They're hard to write, they have derivatives in them, and they're a little hard to wrap our heads around. And so a more useful expression for the reaction velocity is what's known as the rate law. The rate law is given as the form, if we have our reaction A plus B goes to form C. Our rate law is given as the reaction velocity nu is equal to K times the concentration of A raised to the X times the concentration of B raised to the Y. This nu, this is our reaction velocity. So it is the rate of the reaction. K is what is known as a rate constant. And it is a coefficient that is proportional to the reaction velocity. So this is sort of a scaling factor, I guess would probably be the best way. It is concentration independent. Now, X and Y, these are related to the reaction order. The overall reaction order is the sum of X plus Y plus Z plus A plus B, if we have more reactants involved. These values, X and Y, these are experimentally determined. Okay. And with this, we find that the rate constant is a function of temperature. And so this rate law is only true, and the rate constant is only a constant if we are at constant temperature. Okay, so in the next video, we're going to talk more about collision theory and kind of the backbone and the basics of what we mean by studying these reaction rates.